Everything is now being recorded.
Saturday, first day.
Yeah. Sadness.
All right, my friends, let's come together. Brought the bell. Let's use this as our focal point. Just let the waves roll through you and dive into the sound. And then when it's gone, we will start. Old man ears can no longer hear it, so it is gone. So, friends, let's see. I hope there's a lot of questions today. I hope and pray we have, oh good, that's good. That makes me happy. So, that's good. Everybody should be working at least as hard as I'm working at the class. That's excellent. And we have a quiz on Wednesday, right? And there might be questions about that. I'm certainly going to talk about some of that stuff today and on Wednesday. What can I do for you first? What would you like to start with?
I'm just not sure how to plot out the inversion function.
For which problem?
Any problem that requires plotting?
So the ones where you invert the circle or the line into the circle? Wait, just give me one. Give me some concrete.
Just like, for example, like number 6.
So, I mean, there's basically two formulas you need. You need to understand this formula is the formula of a circle. That's a circle of center, x naught, y naught, radius r. And you know the equation of a line. So we have all the stuff we need. Hold on, let me think. I can't remember what we talked about. We talked about taking this thing, so a line, and converting it into this form, right? So not a problem with that. Well, once you get it into this form, you're going to have something that looks like this. So get it into that, and then literally just go to the formula equivalence. It was part of that quiz. How do you read off what this is? If C is non-zero, then we know it's a circle. And we have a formula in one of the theorems for how to find that center and radius. So just use that. I wouldn't go through and crank it out by hand. That would be horrible. That's what that theorem is for. Does that help a little?
But what if it's a line?
If it's a line, we also have another theorem that says if I have this, what is this line? And we have one, I think, let me look. Somebody can help me out here if you can find it for me. Yeah, it is on page 30. It tells the equivalence between the two lines. So for example, let's say I had this and it looked like this. Let me help you go backwards. So Vivian, on page 30, lines and circles in C, let's say I got a line that is 1 minus IC times 1 plus IC plus, I don't know, 2 equals 0. So your question, I guess, is how do I plot that? So what I would do is do the inversion. We know here that this is, let's write out what we do have from this theorem. We have that this line here is equivalent to this, Lordy, if alpha is 1/2 a minus bi. So we know that from just that result on page 30, that if I have this, I can go here by just making that switch. So how do we go backwards is really the question I think you're asking. So let's come over here. This is my alpha, right? This is my alpha here. And I'm just going to say, okay, so alpha, 1 minus I is equal to 1/2 a minus bi, and alpha conjugate, so this is alpha is this, and alpha conjugate is 1 plus I, I'm just literally just taking that conjugate there, and that is equal to, I don't know if this is gonna help me here or not. Let's take a look and see what's up. I think these might actually just say the same thing. That's alpha conjugate right there. And so, oh, I mean, I could literally, and you only need one of these. You can read off what A and B should be from here. Because 1/2 A is 1, so A equals 2, and negative 1/2 B equals -1 over here, so B equals 2. And then I just go, and this, and D is always this number, so that's in common, so this thing must be 2x plus 2y plus 2 equals 0. You see how I did that? Cool, so. It's something we haven't done in here for sure. We definitely haven't gone in that direction.
So you just need to go backwards.
Yeah, totally. Just grab this thing alpha here, and your A is twice that number, and your B is negative twice that number there. Yeah. Is this cool? Good. Okay. So that's a good start. What else we have? Yes, ma'am.
So for number 8, it gives us an equation of a circle.
Okay.
And I just want to know if I started it correctly. Can we solve for y and then use the line equation?
Can you remind me what that question was, Ms. Kintra?
Determine in standard form the image of the circle C given by, and then the equation under inversion of the unit circle.
Oh, so for that one, I would literally just use the formula. So there's a formula, problem 7, which we did not assign, it did not assign. To do number 8, see number 7. It'll give you the formula. Does that make sense?
Yes.
Yes. Cool, good question. Other questions?
This doesn't really relate to the homework, but with stereographic projection,
Yeah.
for like the quiz, I was getting confused on like what point is the original point and what point's the image, because like when I looked it up, I got like something different.
It's cool, yeah. So I'm glad you asked this. For that part, so part of the quiz is, what is stereographic projection? You don't have to know the formulas for the conversion.
I was
painful. And that's maybe not your problem?
more so just like conceptually, like, is it like a projection from like the XY plane onto the sphere, or from the sphere onto the XY?
It is both of those, my friend.
Okay.
Yeah. So stereographic projection, you can do this 2 ways. The way our book does it is we take a unit sphere and we sink it into the plane. So that this plane, and so that's kind of cutting through right in the middle there. The point on top, the equation of this sphere, we imagine it in 3 dimensions. So let's say that's x, back I can do x, y, z, y, and z. And so x, y is the plane, the complex plane. Z is this new thing we've added to make a sphere with. The equation of that sphere is that, it's a unit sphere. And the way this, so we call the top here the North Pole, bottom South Pole, and the plan is this. Pick a point in the plane Z, draw a line from the North Pole to the Z, and wherever it intersects here, that is its representation on the sphere, and vice versa. The representation of this in the plane is that number there. And that's really all I want to know. Does that help? Does that sound a little better? Yeah, what were, you want to talk more about it, or?
Well, I guess like the reason I got confused was because like when you go into like Mobius transformations, it talks about doing like a stereographic projection, and then like the inverse. Is it just like, I guess, conditional then? Like,
Yes.
okay.
Yeah, and we're going to use this to kind of understand how Mobius transformations do some things that they do. Like, it's really easy to understand inversion with this thing because it's basically flip it upside down. And then whatever was on here, so if I had this weird little triangle on here, and then that corresponded to something out here, like that, and then maybe that corresponds to that. Well, that's not bad, is it? Then what is the inversion of this in the unit circle? I just turn this thing upside down and then figure out what this image, so it would be down here then, right? If I take this sphere and I turn it upside down, this thing, and kind of twist it around or something, that's underneath there then. And then I figure out what is its image inside. Notice it'll fall inside the sphere because the stuff that's underneath, when you draw a line from the North Pole to the bottom half of the sphere, it's inside the unit circle. So then wherever this intersects inside here would be its inversion. Does that help?
Yeah.
Only thing I care about, Christian, in terms of this is you understand this picture and how to move from there to there. What is the basic setups? Don't worry about the conversion. You don't memorize the conversion formulas. If you did, awesome.
Sweet.
Does that help?
Yeah, that answers my question.
Oh, cool, awesome. Other questions? Grace.
Number 9, it's the true and false one.
Ooh, what is this? Can you read it to me, please?
If a circle C gets mapped to another circle under inversion in the unit circle, and the center of C gets mapped to the center of the image circle. If the statement is true, prove it. If it is false, provide a counterexample.
Cool, what do you think?
I mean, I would assume true, but
You would assume which one?
true.
It feels like it should be true, doesn't
Yeah.
it? Let's see a way we can maybe get a handle on this. So one way to get a handle on this are those conversion formulas. If I take this, oh my God, I'm so hungry, it's just hitting me right now. The jelly beans are not cutting it. It's probably diabetes setting in. It's feeling it subtle. If we look at the conversion formula, which was the one I was referring Vivian to, I believe, or yes, no, someone, can't remember who it was. No, maybe it was, but I was answering the wrong question, Vivian's. Yeah, so, number 7, that was Kintra's question. So if you look at question 7, it says that if I invert this in the unit circle, the equation of it is this. And as long as this doesn't intersect the unit circle, it's going to be x minus x naught over d squared plus y minus y naught over d squared equals r over d squared, where d is equal to a squared plus b squared minus r squared. So that's problem 7, gives us that formula. So now I can say, okay, here's a circle up here with center x naught, y naught, of radius r. Here's its image. Does the center of this, so we've got here a couple things here. We've got this complex number x naught plus iy. What is its inversion? We can find that pretty easily, right? Just simplify that. Is that the same as this center that we're getting here? Because it's saying the inverted center of that circle is this thing. Is this the same as that number? So does the predicted center actually mesh with the center I compute if I just invert the center? Here's another way to see this. This might be helpful, and this comes from a conversation Lou and I were having before class, or before a couple of classes ago. Take the unit circle, and heck, Lou, I'm gonna totally kind of rip off the stuff we were talking about. Let's take a circle out here. Oh, I won't make it exactly Lou's. No, that is Lou's. Oh, let's do 6. So I got one out here at 6, and oh, heck, it's got a big old radius, so that's 4 right there, and that's 10 on the real axis. So I've got this circle of radius, what is that, 2? Yeah, okay, now it's better. So we can just think in terms of the real axis. What is inversion on the real axis? Well, if I have z out here and I do 1 over z conjugate, it's just still on the real axis because the conjugate doesn't change when you're on that axis. So you could just think of this as on the real axis, inversion is literally kind of just like what I expect. So when I invert this circle into here, what does 1 over this go to? Where does 1 over this, and what is 1 over this? And you're gonna get 3 points inside here. Is this still the center of those two? Does that make sense? That's probably the easiest argument, I think. Yeah, I like that argument a lot. There's this one nobody's asking about. Very concerned. Everybody's looking. What should I be? Which one could he possibly be talking about? Which one could I be talking about?
Just let me clarify.
Yes,
So
ma'am. Yeah.
We're proving that that 1 over x naught plus y naught, you're standing like in front, no, the other way.
We're proving that when I invert a circle in the unit circle, we're deciding when I invert this dude here into here, it becomes another circle with that formula.
Yeah.
Does the center of the original circle get mapped to the center of the inversion? So in other words, this circle over here of radius 2 centered at 6, when I invert it, is its center this 6 goes to 1/6, but is 1/6 the center of that new circle? Does that help? Yeah. I don't want to spoil the fun. There's not much fun left. There's a little bit of fun left. Did I not assign the problem I'm thinking of? Well, let me have a jelly bean look. Did I assign problem 4?
No.
What? Are you serious?
Yeah.
5, 6, 8, 9.
Got it. Let's talk about problem 4. Dang it. No wonder no one's asking about it. I was like, how can no one be asking about problem 4? Well, now I see. Now I see everything. And maybe this, so that actually probably does answer all the questions that might be outstanding the homework? Cool. Why is that thing due on Wednesday? That seems crazy, but whatever. So look at, if you wouldn't mind, I'll write it up here, but I'm looking at section 3.2, problem 4. Because we need this fact either today or Wednesday, one of the two, it's gonna pop up. So this is page 54, number 4. We have T1, ooh, that's a fancy T. T1 equals inversion in this circle. That's a circle centered at the origin of radius R1. So that's this dude. Could be any of these dudes, but that's R1 right there. And then T2 is inversion in another circle that's concentric with that one. Z equals R2. We don't know if R2 is bigger than R1. Let's just say R2 is bigger than R1, so that R2 looks like this. So that's my R2 circle. And T2 is inversion in that circle. So the problem here is prove that if I compose, if I first invert here, then invert here, all I've actually done is scaled. This is a really cool fact, and it harkens back to some of our first days together, those early days, the limerence of this class, the cusp, the dawn. Remember how we talked about if I reflect over two parallel lines, that's a translation. That sounds familiar? I hope so. That's good. If I reflect over two lines that intersect at the origin, what do I get? A rotation. So I get that, reflect there, you end up getting a rotation. So translation is two reflections, rotation is two reflections. This is saying scaling is two reflections, just over circles. So how could we do this? Well, we would use our formulas. Here's a quick little proof. This is a scaling. What is? T1 composed with T, let's do T2 composed with T1. Let's do 1 first, is a scaling. In other words, i.e. T2 composed with T1 of Z is just some constant times Z. Just sends you in the same direction, just either stretches you or shrinks you. So let's see this. Well, what is the formula for T1 and what is the formula for T2? Can you kind of just take a minute and see how much you remember about that? You know, without looking it up, we can look it up. You had a quiz on this when you had a circle of center Z naught. Let me start just shaking your brain just a little bit there. Everybody remembered that pretty well. What is the formula for T1? Tara, do you know that one? I'm gonna start calling. I got it. Oh, I came up with a new thing. I'm gonna start calling on people.
Like the entire formula, or is it like the center and then the radius?
Yeah, so yeah, what is the formula here? What was the original, like just here? Do you remember? And I'm putting you on a big spot here.
I want to say it's C, Z conjugate. Oh, it.
Oh no,
the
actual formula for cranking out the inversion. Yeah. But
R,
you were
okay. R squared over Z minus Z naught.
conjugate. There you go.
Yeah.
Yes, thank you, friend. Good job. You're off the hook for the rest of the day. Good work. So here we've got Z naught is 0. We've got r as these various radii. So T1 of z naught is going to be r1 squared over z conjugate, because z naught is 0. T2 is r2 squared over z conjugate. Let's put them together. Can you take a second and do that, please? Can you please crank that out and simplify to the best of your ability what that's going to look like? No wonder nobody's been asking about that. I've been laying awake at night. Tossing and turning. Got it up here. Just make sure this makes sense to you. It might take you a while longer. That would make sense. Anybody want me to talk through that? Yes, sir.
Why don't you conjugate like the r1 squared?
Oh, what an awesome question. That's a great question, Christian. Does anybody have an answer? Kendra.
Is it because there's no imaginary part to it?
There's no imaginary part, exactly. So the radius of a circle is a positive real. Great.
That
Solid.
makes sense.
There we go. Put the knowledge together. Thank you. Just a little bit of computation, reciprocals and conjugates and stuff. But it turns out that if you do this, it's a handy dandy way, because think about how inversion works. It's just on a line, right? So if that's z, and then I flip to there, and then I flip to there, I'm just scaling myself along the same line. And depending on the ratio of the radii, we're going to get a different scaling factor. If R2 is bigger, like I've drawn it, you actually expand. This is a greater than 1. If R2 is less than R1, I'm shrinking. So if R2 was inside R1, I would have shrunk myself a little bit. Cool. Okay, well I can stop losing sleep over that. I really have been thinking about it. This is like I'm out walking dogs. I'm like, why is nobody asking about or how could I not have assigned that to you? Does this make sense? Is this cool? Anything I can help with here? Okay, cool. All right, is there anything else like quiz-wise stuff that, I'm gonna talk about it all today. So I think you might feel better about it, but if you have something like Christian had a question about it, that probably took a lot of weight off you,
I
right?
was like trying to figure that one out.
Yeah. Yeah. They can also do those stereographic projections by putting the sphere on top of the plane. So sometimes they do that. This guy's just sitting on top of the plane like this, and your North Pole is actually at 0, 0, 2 in the XYZ coordinates, and then the South Pole is the actual origin before. It's the center of the complex plane. Works like that too. You can absolutely do stereographic projection in the exact same way. You just get different coordinates. It's all about plunking a ball in the middle of the plane, drawing a line from the North Pole. So no other particular questions? Let's see, so let's just recap really quick what we need to know for that quiz on Wednesday, and then we'll get busy talking about some of it. So you need to know, what is a stereographic projection? I hope now you've got some things to say and draw about that. If you can't draw a sphere, you know, that's cool, but got a sphere drawing would sure help, right? Here's how you draw a sphere, just in case you're worried. Draw a circle, and I'm not being a smartass. Draw a little smile for the equator. Draw a rhombus behind it. Done. And you can then you can go like this. Look, it's sunk. Now it's sunk. You can't see that part. So that's how you do that. Here's how you draw a donut. Draw an oval. Make a smile. Do that. These are two of my favorite drawings. There's a nice torus for you if you ever have to produce one. And you won't here, I don't think. So more than anything, I think that question is, can you draw a sphere and a rhombus and a line and talk about them roughly? Then the last one is, what is the formula for the inverse Mobius transformation? You need to know what a Mobius transformation is. We're going to talk about that. Problem 2 on page 67. Maybe we'll talk about that. Theorem 3.48. What the hell is that? Well, let's look. Theorem 3.48, and then we'll talk about all this stuff today. The fundamental theorem of Mobius transformations. Any 3 points mapping to, there is a unique Mobius transformation that takes any 3 points in the plane to any other 3 points in the plane. That's all you have to know for that one. Just statement, you don't need to know the proof. Definition 3.410 is the cross ratio of 4 complex numbers. I'll be sure to work an example of that today. That's a simple computation. Know that formula, the cross ratio formula. We'll talk about it soon, today. Be able to crank out some stuff. So the last thing is page 67, number 10. Do these points. They give you 4 points, Z1, Z2, Z3, and Z4. And the question is, do these live on the same line in the plane? If I plotted these out in the plane, do they fall in a line? Well, fix it up. Do they fall in a line? How do I know that? I take the cross ratio of those 4. We may or may not know what that is. And if that is real, if this is real, then yes, that's it. So that's good. That's a good idea.
So the cross ratio, does that just tell you whether or not like a given amount of points are like on the same line?
Yeah, the cross ratio tells you, the cross ratio is a crazy beast. But one of the things it can tell us is this, that if this quantity, let's talk about it. So the cross ratio. And let's talk about what it is. The cross ratio for complex numbers. This is on page 64. It is definition 3.410. So the cross ratio, you've probably never encountered this. Even in complex analysis, folks, we've all been together through that, we didn't talk about this. This was not part of that class. So the cross ratio is kind of between 4 numbers, but in a way it's between 2 pairs of numbers, but we'll just pretend it's 4. And it is a product of 2 quotients. So you take Z1, they use nice letters, they don't use subscripts. So you take that minus that. So I take Z1 minus Z3 over Z1 minus Z4. Notice the rhythm there. So this minus this over this minus this times. Now we move, notice Z2 hasn't been spoken of. Now we do it in the reverse. Z2 minus Z3 over Z2 minus Z4. It's just a simple rhythm. Luke, question?
Do you have the second half like flipped? The Z2 minus Z3 over, should it be the other way?
Oh yes, thank you. I pointed to the wrong shit. Yes, it's backwards. So it's, if this one is that minus that, that minus that, then the second one is that minus that, that minus that. Thank you, Luke. Yep. They use UVW. It's a lot easier that way, in a way. So just practice that rhythm. So let's answer a question. I'm gonna leave the one in the book for you, but let's just see. Let's make up a problem that we know the answer to and test this all out. So, what do we got? Let's pick 1 plus I. Let's try, wish I hadn't done that because it's kind of lame. And then minus I, so notice I have a line now of slope 2. So the next point is going to be 2 plus 3I. And then let's go down this way and let's just crank these things out. I wonder what that point would be right there. What would that one be? Right there. I don't know what the hell that is. What would that point be right in the middle there? That's just 1/2. So, and 1/2. Let's plunk a real one in there so our life isn't so hellish. So let's find the cross ratio of these in any order. 1 plus I, minus I, 2 plus 3I, and 1/2. What is the cross ratio? And it really is a complicated thing. This is just one application. Might hate me after this. It's just maybe not the prettiest thing in the world. I'll try to come up with some better numbers for the quiz. But in the end, it's just foil, so it's not too bad. Good Lord. I'm going to simplify my life. The key thing here is we end up with a real number in the end. So what that's going to look like is one of these is a multiple of the other. That should be what we end up with. The top is a multiple of the bottom, but we'll see. looking pretty good. Pretty damn on track to be multiples of each other, I would say. Alright, so let's just make sure. This would be a good practice one. Make sure that you can do this, and then I'll send you all solutions to that other one tomorrow morning. Do you see why this is real? Grace, would you mind telling us just the why, please?
I mean, the top is just a multiple of bottom.
Yeah, if I do this division, it's literally, the top is twice the bottom. Like, look, the top is just twice the bottom, so this is negative, the original negative, and then times a 2 here. So the answer is -2. You can suffer your way. Lou, you're making a very furrowed brow. What's up?
I don't know. I was feeling like it was a half. Because the bottom.
Oh,
twice
is
as
it?
much.
Oh, you're right. Yeah, you're right. The bottom is twice the, yeah, thank you. Hey, thanks for the brows.
I really thought I was wrong.
You're
so-
not, you're not. I convinced myself of some bullshit. Yeah. Yeah. Yes, that's right, yeah. It's confusing. Yeah, yeah. As long as you can say the top is the multiple of the bottom, you're good to go. Because that's just a real multiple. Does that make sense? Yes, ma'am.
Would you get a different number if you solved the fractions individually before multiplying them?
Problem. You shouldn't get a different number. No.
Just curious.
Yeah. You shouldn't get a different number. You will get a different number if you permute them. So if we had done these in a different, plugged them in a different order, I would probably get a different number out here. But yeah, if once I have that set up, Kitra, no matter how I do this computation, I'd better get that. And I obviously need Lou around to do it, so. Good question.
Does this work for like all clines, or is it just like lines?
Just lines. Oh wait, does it
says
say clines? Does it say all clines? I think it might be all clines actually, yeah, if we're on a circle. What was the statement of the problem? On a single cline. Oh, do these, yeah, let's see where these guys lie, because I think actually you're right, Christian. It might be true for circles as well. Oh, let's have fun. Come on. Let's see what we got here. Let's see if it works for clines. Let's pick the simplest cline of all. Can we find the cross ratio of the 4 cardinal points of the unit circle, please? Let's just see together. I'm excited. Thanks, Christian. Damn good question, man. And in any order you want, I'm gonna start with -1 and work clockwise. So it'll be interesting. I hope somebody does it a different way. We see if we get different answers. This is actually good practice for the rhythm as well. So far, so real. Not bad. And then we're gonna do so I think the answer is yes, this works for all clines, yeah. And then we'll see something that really cool that, whoa.
Yeah, you have to
Whoa. We got 0 there, don't we? Isn't that 0?
Yeah, but wasn't 1 supposed to be -I?
Well, it's not in this first one. In the first one, it's,
Numbers.
I'm sorry, say that
You're
again.
missing it.
You're missing an I.
Yeah.
Am I missing it now? Oh, okay. So what did I do wrong? So let's see, I took this is Z1, I took it minus Z.
In this set of numbers,
Yeah,
you
like
have
one
3
should be
ones.
moved.
Oh, thank you. Oh shit. Okay. Yeah, that'll do it. Hey, solid. Thank you, my friends. I can't really do anything without any of you, I guess. Let's just stay here forever. All right, so let's come back and do it again. Z1 minus Z3. Yeah, that was scary as hell. Z1 minus Z4. Yay. It's C2 minus C4, so yeah, it's true. Oh, so it's like pairs. So the first pair is these two, and then the second pair is those. Okay. Minus I all over I minus 1. I think that looks hunky-dory. So we're going to make it 2 negative. Multiply. Yeah, now Kitra, I'm actually just gonna plow through, and because these two are nice and chill to multiply out. So on the top I got negative 4i, and the bottom when I foil, I get negative 1 plus I plus I. Oh, that's good shit. And plus minus I squared. Yeah, -2, looking good. Watching your brows. Little Geiger counter. Did anybody get something besides -2?
I did mine in a different order.
You did it different, or what'd you get?
I got -1.
-1, cool. What order did you do?
I did I, -I, 1, -1.
Cool, cool. Did you get a different one, Lou? Did you?
I also got
-1,
I
cool.
got 2.
2, awesome. What order did you do, Tara?
I, 1, -1, or sorry, negative I, and then -1.
Awesome, cool, cool. Oh yeah, that's, yeah, okay, cool. As long as we get a real, it's all that matters. So that's actually pretty powerful. Just crank this number out and you know if they're on a circle or a line. You don't know which, but you know they are on a circle or a line if that quantity turns out real. That's pretty cool.
Wait, can you clarify, like, either way it's a circle or line? Or
Yeah, so let me write up a little statement here for you. So if Z1, Z2, Z3, Z4 is real, then the points, then these points, then those points lie on the same cline. That gets us covered. Yeah, thanks for asking that. Neat. I want to make sure that we talk about the things that are on that quiz. There's other things I want to talk about, but I really want to make sure primarily we talk about the stuff on that quiz. So let me make sure to address Mobius transformations, unless there's any more questions about this. Well, I tell you, one of our candidates, one of the things, that's all over. We will hopefully have the answer by Wednesday. God, I hope I know Wednesday who our new math professor will be this fall. But one of the things people really didn't like was when people didn't give time for questions. They freaking hated that, like across the board. Fair enough. So maybe I'm getting a little too crazy with it, but you know, if I'm safe, I can't get fired. I have to be really stupid. I can't get fired. I shouldn't say that. I can get fired. I just have to be a monstrous asshole to get fired. So. I'm gonna try to avoid that. Just stay clear of this like monstrous asshole. That's all terrible. I'm so sorry. Let's talk about Mobius transformations. So first off, it's Mobius transformations. You got that umlaut, like, what do you call it? Is that an umlaut? No. What do you call that thing? The dots? Anybody German, Dutch? Accent, double data, something. I don't know. It's some kind of weird German thing. Mobius. Mobius transformations. And Mobius did a lot of stuff. What else do we know Mobius for? What is Mobius known for, mostly? His strip act. Yes. Mobius is mostly known for, what is this here? Okay. Mobius is mostly known for the famous strip. And you take a piece of paper. I don't have enough tape. We're doing this. Oh my God, we're gonna do some stuff on Wednesday. You take a piece of paper, you give it half a twist, join the ends together. A Mobius strip, a single-sided object. Non-orientable object. I highly recommend to you before Wednesday, just so you can have the fun of doing this, make a Mobius strip, cut it down the middle in half. Oh yes, it's very cool. And then make a new one and cut it in thirds. Start cutting a third of the way across. Just keep going and keep going straight and keep cutting straight and see what happens. So if you've done the half, which it seems like you might have,
I think it was in calc.
Was it in calc?
I think.
Did you do thirds?
I don't think we did those.
Oh, do thirds. Do thirds. This is good stuff to do at home. Okay, so that's the Mobius we know about. This is a different Mobius that you don't really see unless you do complex analysis, in which we barely talked about these. Is a transformation that looks like this. It is called a fractional linear transformation if we don't like saying the sound. So this is also linear fractional. I think I said fractional linear, but what I meant was linear fractional transformation. Linear fractional because it's two linear things in a fraction. So it helps to remember what we got going on here. So these are of utmost importance to us in the study of geometry in the plane as we move forward. In fact, there's a whole geometry, which we still don't know quite what that is, of what a geometry is, called a Mobius geometry. So let's see, where do I want to go with this? Because I do want to make sure. So these operate, we will think of these operating on the extended complex plane. You really should read the book if you are not reading the book. I should not be the only one reading the book multiple times, and I'm still reading the book multiple times. You should be doing that too. Extended complex plane is C, our good old friend, unioned with a new point called infinity, the point at infinity. So we toss in this point at infinity, and you're like, how can this be? Well, it can be because of the Riemann sphere. The Riemann sphere is a model of the extended complex plane, and you can get to the top. You can get to infinity. It takes a long time, but you can get there. So what about this new symbol, this infinity, that's at the top, the north pole of the Riemann sphere? Well, first off, just notice that no matter what, oh my goodness, that egg, tuck that egg in there, that no matter what direction you head out in, and I showed you this on that app the other day, no matter what direction you head out on in the plane, its projection back up to here is approaching the top. So if this is the plane, head on, no matter which way you go, you are going to a single place. And that's a brain stretch. That's mind bending and space bending, literally. Literally takes space bending to see that. This infinity has some properties. We will say that infinity plus any finite number x, so x is any complex number that's even infinity, is infinity. Now don't try to solve that. This is some weird shit, because if you try to solve that, you say, oh, x must be 0. That's not what we're saying here. We're just saying we got this weird new symbol that interacts like this, and the normal rules of arithmetic do not apply. So 1 over infinity is 0, and 1 over 0 is infinity. 0 is at the bottom of the Riemann sphere, and inversion flips these two. Inversion is 1 over. So we're just flipping those two. They trade places. And I think that's all that I want to say about infinity for right now, because, oh, and I want to say one more thing, inversion. So let's think about inversion in a circle. We've got a circle, center Z naught, radius R. The inversion formula that Tara gave us a little earlier, inversion in this circle C of Z now has a new form. Remember how it was basically Z naught plus R squared over Z minus Z naught conjugate. That's if Z is not equal to Z naught. So if you're not at the center, then this is the inversion. If you are at the center, how do you invert the center? Well, the center turns into infinity. And what if you're at infinity and you're inverting? It becomes the center.
Does it say for the middle one?
Yeah, that's a good question.
Z something?
It says if Z is not equal to Z naught. So if you're not at the center, use the normal formula. If you are at the center, the inversion is infinity. If you're inverting infinity, it pops into the center when you flip over. So now that we have that, we can really worry about this Mobius stuff, because we can use infinity like a number, and it's really quite lovely. So let's come back to a Mobius transformation. Have I said, please read this section? Okay, please read this section, because I'm not saying some things that are in my head to try to keep this a little cleaner. What if C equals 0? What does this thing turn into?
Z plus B over D.
Yeah, it's kind of, it turns into this. So if C equals 0, this turns into just A over C, A over D, Z plus B over D, right? We've still got that D down there, so like that part goes away. And we just have a linear transformation. So we have a linear transformation. A linear transformation involves scaling, rotation, and translation. So if C equals 0, we know about this. We spend a lot of time with this transform. If C is not 0, then we got some fun stuff going on. So let's focus on the case where C is not 0. Because then we got then we have a linear part on top and a linear part on the bottom. We have a fraction of linear things, a linear fractional transformation. So we're going to focus on this. Now, what's T is 0? What's it? B over D. Beautiful. Thank you, Vivian. Cool. Does that make sense? Just plugging that shit in, right? Crank it out. Anyone care to hazard a guess as to what happens when I plug infinity in? what happens? Think calculus. Think calculus. Go back to your calc class and you would get something like this. Well, Jesus, okay. How do you do that limit in calculus? What's that?
It'd be 1.
It would not be 1.
A over C?
It would be A over C. It would be 1 if A and C were the same. So it's the ratio of these coefficients from good old calc days. Infinity over infinity. How did you do that in calc? What rule?
Yeah.
Yeah, L'Hopital's rule. So you could L'Hopital that and see that it was also A over C. So that is our answer here. It's just, you got this. Imagine the Z is a giant ass number. What is A times a big thing plus B over C times a big thing plus D? Well, if this thing is big enough, if this thing is like a Google, C times a Google plus D, this shit don't matter. Those don't matter. Once I've got A times a Google plus a tiny bit over C times a Google plus a tiny bit, all that matters is this stuff here. So that's how your prof hopefully explained why this would also turn out to be A over C. Can you help me solve this? What's the solution? Take a minute. Would you say something? Well, if I put in 0, I get out B over D. So no. Yeah, and a good thing I should note is that A, B, C, and D are not, none of those are infinity. They're just finite things. Morgan, you think you maybe got a sense of that? And here's the hint. What gives me infinity in a fraction? 0. 0 in the denominator, right? So what would make this denominator 0 here? I'm asking you to solve an equation on the spot. So in other words, what Z solves that?
Well, I mean, initially I just was like C0 and D0, but.
Yeah, that would totally do it. Yeah, that would be, yeah, you're right. But let's say they're not 0 and we got this. What is the solution to that dude right there? What Z makes that true? I think you're thinking too much here about, you're getting too many infinities. So just take this subtract D from each side, and divide by A. So if Z is negative D over A, I blow up the bottom.
Was it supposed to be C, not A?
Probably. Which might be part of why it was confused by my question. Yes. So whatever makes this bottom, which is negative D over C. So Z equals, and so we can put that in here, negative D over C gets sent to infinity. And now I've got one last one. Could you tell me, what do I got to put in to get 0 out? I'm going to have Miss Olivia help me with that one. What makes, so we got a fraction here, let me help. Got a fraction here, it's 0 when the numerator is 0. What makes that numerator there 0? What's Z value?
Negative B over A.
Solid, yeah, you got it, you got it. Beautiful. So, these are all the ways infinity and 0 can manifest in a Mobius transformation. If 0 or infinity come in, it's either this over this or this over this. If we want to figure out what gets sent to infinity by this transformation, what makes the bottom 0, what gets sent to 0 by this transformation is just what makes the top equal to 0. So let's take a look at a couple problems that I said you might want to look at. And those are problem 2, page 67. Oh, shit, we got one more to do. That's something different. I don't want to talk about that yet. Problem 348. Well, I guess we almost have everything. What's page 67, number 10? What's that? No, we got that. Okay, I think we just about got everything, almost. There's one last thing I wanted to talk about, and then we'll be good, and you'll have everything you need for the quiz, except like learning it and practicing it. And then coming in on Wednesday and asking questions, or asking me to make up more examples, or telling me what you need before then. So, this thing here, the one thing I didn't say is there's a special condition on A, B, C, and D. So T of Z, let's write this up again, is a Mobius transformation. I got too excited and all my umlaut nonsense. Mobius transformation. If one condition is really important, A times D minus B times C is not 0. Does that, hello DiffyQ friends who were just in here with me an hour ago, does that even look familiar? Yeah, Tara, what is that?
It was to see if there was an inverse.
It's the determinant of a 2x2 matrix. So notice that this, if I gave you a matrix A, B, C, D and said, what is its determinant? It's that thing. A times D minus B times C. You add those. That's the determinant formula. And that's when, if this thing is not 0, that implies that you have an inverse matrix that exists. Then you can find the inverse if the determinant is not 0. Same thing here. We put that condition on so that we can find an inverse. Wait till you see how easy the inverse is. So for a normal matrix, the inverse is you flip these two and then you negate these two things. For a Mobius transformation, the inverse, don't write this down, please, because I wanted to see if what I just said is absolutely true. I'm starting to get scared that it's not. I'm just gonna look it up. The inverse transformation is, are you reading it there? Do you see it in front of you? Lou?
Oh, I can just tell it.
Yeah, why don't you just please tell me it?
Negative DZ plus B over CZ minus A.
Oh, so these two become negative. So it actually is a little bit different. I don't know, yeah, it's a little bit different than I was thinking. So that's the inverse formula. Let's just check out a couple of things. If the original transformation acts like this, 0 goes to B over D, notice that here, T inverse of B over D is what? You put in 0, you get a 0 on top. Replace this Z with B over D, 0. So all these other things are going to come true. T inverse of infinity is what? Do it on that one. What's T inverse of infinity? Negative D over C. That makes sense with this. So these relationships here parallel these over here, and we can figure them all out just by looking at that form. We don't need that information, but just to see it side by side. That is everything that will be on your quiz. So on your quiz, just know this formula, know this. That's the definition of a Mobius transformation, know that. Know that formula. This formula automatically works once we have this true, so we're always going to have it true. And I think you're probably good to go. Let's see, that's problem 2, page 67. Please work that one on page 67. Number 2, literally use this formula to find the inverse. I'll send all the answers out, and then do problem 10, and you should be good to go. And you let me know if you have any troubles, and I will help you, okay? And let me know what you need on Wednesday. If you need to talk about any of this, you gotta tell me. Thank you, friends. Thank you. Hi. Let me shut down. What's that? Whatever, I don't remember quite off the top of my head. I gotta go look. They're in the,